In this video, we're going to talk about just the very basics of renal function. Sort of like what jobs do the kidneys fulfill, and then we'll provide you with a summary of how urine is formed. So, what are the basic renal functions? Let's list these. All right. Well, one thing that might jump into your head is ion regulation. Right? Ions constitute one of the major small solutes in extracellular and intracellular fluids. Of course, the kidneys are only regulating extracellular fluids directly. And ion regulation has a lot to do with helping to maintain membrane potentials. And the reason this is true is membrane potentials are all about ion transport across the membrane, whether it be active or passive leak, and it sets up a voltage. And that voltage is generated by the charge of the unequal distribution of ions. And of course, if we upset the ions in the ion concentrations in the extracellular fluids, we upset that separation of ion concentrations and therefore charge, and that would, of course, mess up our membrane potentials. So that's a major function of the kidneys that can cause serious problems very quickly if the kidneys are not doing their job. Another one that's probably fairly obvious is fluid regulation. And the reason fluid regulation is so important has to do with a couple of things. One has to do with blood pressure. And if you think back to the cardiovascular section, blood volume is a major determinant of cardiac output. And of course, cardiac output is a major determinant of blood pressure. And so blood volume and blood pressure are intimately linked, and the kidneys are one of our major sources of regulating how much fluid we retain or excrete. Another one would be basically body fluid osmolarity. And that's true of the ion regulation as well, but it's even more rapidly regulated by fluid regulation. So body fluid osmolarity, meaning concentration, right? So in other words, if we were to excrete too much fluid, if you were to take a diuretic, and your body fluid volumes were to fall rapidly due to a large urine volume being produced, the ions in the remaining body fluid would become more concentrated, right? And so by regulating the fluid, we're actually regulating osmolarity, because if you'll recall, osmolarity is the amount of solute relative to the volume it's dissolved in, right? And so regulating the volume or the solute, and again, that's where we go back to ion regulation, one of the major solutes in our body fluids. Regulating either one of those will alter body fluid osmolarity. Okay. Another major function of the kidneys is long-term pH regulation. And remember, this one always sort of boiled down to protein marginal stability. And again, what we mean by that is that proteins are susceptible to disruption of their structure due to interaction with largely ions, but other molecules as well. And pH regulation is really all about, right? It's really all about H plus regulation, which of course is an ion, and therefore has the potential to interact with proteins. And so if we upset the normal concentrations of these ions in solution, i.e. our pH, then we start to disrupt the marginal stability of proteins and therefore their function, right? And of course, that can be deadly. And then probably maybe even number one on your list that you might think of is waste excretion. Right? And for a function, largely it has to do with the fact that wastes are toxic. And when you say toxic, you mean, you could say, well, toxic in what fashion? And that could be in several ways, but one of the key ways that they can be toxic is by upsetting the marginal stability of proteins, right? That structure-function relationship within proteins. Okay, and then the last one that we'll list is hormone secretion. So the kidneys are actually an endocrine structure, right? We don't call them an endocrine gland, but they do contain endocrine cells that lead to the production of several different hormones, including erythropoietin. That was a key hormone that stimulates the production of red blood cells, stimulated by hypoxia, as you might suspect, right? If oxygen levels are low, you might want more red blood cells in response, and EPO does that job. Angiotensin 2, right? We learned about this in the cardiovascular section. It's vasoconstrictive, increases peripheral resistance of the blood vessels, and therefore boosts blood pressure. And again, if we need a reminder of that, blood pressure equals cardiac output times total peripheral resistance, right? Resistance. And of course, resistance is modified by the constriction that angiotensin 2 causes. We talked about blood volume up here with blood pressure regulation, right? Blood volume affects cardiac output, right? So we can affect both halves of this equation to alter blood pressure via renal function. Angiotensin 2 does quite a few other things. It stimulates other hormones. And again, other videos to talk more about that. And the last hormone that's produced is a hormone called calcitriol. And this is a hormone involved in blood calcium regulation. Okay, so those are our main renal functions. Let's now take a look at the figure at the bottom here and get at an explanation of the primary actions that occur in the process of urine formation. Right? So this is basically a summary of urine formation. And so we have, and again, this is sort of, these would be very small blood vessels within the kidney. So this unit that I have drawn down here very schematically is repeated at least 1 million times in each kidney. Right? So it's the microscopic structure repeated over and over that leads to the production of urine. So it's the same 3 processes at all of these sort of micro locations, if you will. Right? And so blood vessels branch and branch and branch within the kidney until you get to the point where they form this vessel called the afferent arteriole. Right? Again, we'll cover a specific anatomy in another video. And this is blood flow in. Then we have this series of blood vessels right here, right? That's known as the glomerulus. So these are the capillaries, right? So we have an arteriole leading into a capillary bed. Those capillaries come back together, but oddly, they don't come back together to form a venule as they typically would. They form what we refer to as another arteriole. And the reason for that is that this second arteriole, if you will, is going to branch into capillaries again. So this is a vascular arrangement known as a portal system. There aren't a lot of them in the body. There's a few. But a portal system is when we have 2 capillary beds in series, right? In other words, it goes arteriole, capillary bed, portal vessel. This is also called an arteriole. And then a second capillary bed. Then we would go to the venous circulation, right? So instead of 1 capillary bed, we have 2. And in a kidney, this makes a lot of sense because we want to do one thing at the first capillary bed and then something completely opposite, essentially, at the second capillary bed. Okay? Now, at the first capillary bed, we want to drive this process known as filtration. Right? So filtration is this arrow, and we know what this is already because we've talked about capillary filtration. Right? Capillary filtration is the process of pressure-driven movement of water at bulk flux. Remember bulk flux? Right? Pressure-driven movement of water and small solutes in bulk across the capillary wall. And in this set of capillaries, the Starling forces, if you recall the Starling equation, the Starling forces will favor filtration. Remember, filtration is the movement, bulk movement out of a capillary. In a moment, we'll talk about reabsorption, which is the movement of water and small solutes into the capillary. That does not happen at glomerular capillaries, right? They are set up to filter only and dramatically, right? And so filtration is actually step one of urine formation, right? So we have this first set of capillary beds. We're going to generate a plasma filtrate. It has everything that's in plasma minus the proteins and, of course, the cells. We don't want to filter and excrete cells. So the proteins and the cells pass through these vessels and come right back out the other side. Small solutes and water will pass through the membrane and become filtered. Now, that's not to say all of the water and small solutes. It's only about 20%. 80% of the plasma would actually basically pass through without becoming filtered and pass into this second arteriole here after the glomerulus. Okay, so filtration is this bulk flux out of the capillary to form a filtrate that's in this structure, which we refer to as the nephron. Right, this guy in green, and actually wraps right around the capillary, glomerular capillaries. Right, so that, and notice it keeps going. Right, we have it sort of dot 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 here. I'm not trying to be anatomically correct right now, but we produce this filtrate at the glomerulus into the nephron. Okay, now you could say, well, that's just what you have urine, right? Well, no, because the amount that's filtered, this contains nutrients, it contains waste, it contains, lots and lots of electrolytes. We can't excrete everything that's in there. Do we want to excrete the waste that we filtered? Yes. Do we want to excrete the glucose and amino acids we filtered? No. Or even the majority of the electrolytes. And so this sort of bulk solution has to be modified. And by the way, the total amount for both kidneys for a day, the volume filtered is about 180 liters. You only have 3 liters of plasma, right? So what it means is that your plasma is filtered over and over and over and over every day, about once every 20 minutes. And of course, you can't excrete most of what's in that. You have to undergo step 2 in urine formation, which is a process known as reabsorption. Right? So in the process of reabsorption, the nephron will take things that were filtered, dump them into the interstitium. Right? We have some solutes here that we can put into the interstitium. Right? And those solutes end up getting taken up into the capillaries. Aha! Because the second capillary bed, they're known as peritubular capillaries. Peri meaning surrounding, tubule referring to the nephron, so peritubular capillaries. And their Starling forces favor bulk flux inward. Right? So the nephron reabsorbs, but then the capillary also, the second capillary bed here, also reabsorbs. And so we take things that we didn't want to excrete and we put them right back into the bloodstream. Okay? Now, step 3 of urine formation, and this isn't always, not everything's reabsorbed, first of all, right? Wastes, there are many wastes that are not reabsorbed, right? It makes sense if you filter them, well, leave them in here. Let them go on to be excreted with the urine. But many things are reabsorbed. Now, having said that, the last step or potential step in urine formation is secretion, right? And that would be this arrow. So secretion is when we take something that was not filtered, this arrow a little fatter, right? When we take something that was not filtered, it didn't pass through here. Just remember that 80% did not get filtered and comes through here. But let's say it's a waste molecule. Well, we can do better than excreting 20% of our wastes on any given pass, right? 20% got filtered. We could actually add to that by the process of secretion. So secretion is the process of adding solutes to the nephron that weren't filtered. Right? Reabsorption is the act of removing solutes from the volume that was filtered, from the content that was filtered. So reabsorption is taking things out of the nephron. Secretion is putting them into the nephron. You want to reabsorb things you want to keep, you're putting back into the bloodstream. You want to secrete things you want to get rid of, right? Organic wastes or protons, right? For pH regulation, we tend to be metabolic acid producers, right? So those things would tend to get pushed into the nephron to enhance their excretion. So we can summarize, and I'm going to block this guy right here, bright red. We can summarize excretion, right? Excretion meaning what you get rid of, would equal what you filter, what you put in here, right? Remember, what you put in here, if you did nothing else, would be excreted, right? So it's what you filtered minus what you reabsorbed, right? You'd have to take that away from what was filtered. That's not going to be excreted. But you'd have to add, see the plus S here? You'd have to add what you secrete. So excretion equals what's filtered minus what you reabsorb plus what you secrete. Now, the reason I have these two equations down here, and this is perpetually right. This is correct. However, for many substances, you don't reabsorb and secrete. You do one or the either, right? So if you want to keep it, there is no secretion, and it would just be excretion would equal filtration minus what you reabsorb, right? And for a waste, you tend to not want to reabsorb it, right? And so we can take the R out of the equation, and now our excretion would equal what's filtered plus what's secreted. All right, and that's a brief summary of the basic renal functions, as well as the steps in urine formation: filtration, reabsorption, and secretion. And remember, reabsorption and secretion do not both occur for many substances, right? It's usually one or the other. Although there's a couple where both occur, which is a little bit strange, but we'll discuss that later.